Today we'll be covering two lessons, Unit 10, Lesson 9, pages 295 and 296, and Lesson 10, pages 299 and 300. You want to have your graphing calculator and a highlighter, please, as well as a pencil or your regular writing utensil. So Lesson 9, Introduction to Rational Functions. Rational functions are a ratio of polynomial functions. Their properties in graphs are different than polynomials because of their interaction between the numerator and denominators. So when we think of rational functions, oftentimes when I think of the word rational, I think of fraction. I mean that its base is ratio, and a ratio can be expressed as a fraction. Exercise number 1, consider the rational function f of x equals x plus 6 over x minus 3. Right, so we have a fraction where the numerator is a polynomial and the denominator is a polynomial. Algebraically determine the y-intercept for this function. Well, for y-intercept, the x-coordinate is 0 and we're looking for the y value. Let's replace x with 0, and we have f of 0 is equal to 0 plus 6 divided by 0 minus 3, which reduces to 6 over negative 3, which is equivalent to negative 2. The y-intercept is negative 2. Algebraically determine the x-intercept of this function. For an x-intercept, we're looking for the x value when y is 0. F of x, remember, is the same as y, so 0 equals x plus 6 over x minus 3. A fraction can only equal 0 if its numerator is 0. Okay, so in other words, what plus 6 would result in 0? Or we can simply cross multiply, and cross products are equal. X plus 6 is equal to 0 times x minus 3 is 0, when x equals negative 6. That is the x-intercept. For what value of x is the function undefined? Undefined is when the denominator is 0. A function is undefined when the denominator is 0. So let's take x minus 3, and x minus 3 is equal to 0 when x equals 3. Based on C, state the domain of this function in set builder notation. In other words, if we look at this, you can put any real number in for x, and it will produce a real number, with the exception of an x value of 3. So using set builder notation, first let me just state all real numbers except x equal to 3. Set builder notation would be the set containing all x such that x does not equal 3. So you can put any x value except 3. Find all values of x for which the rational function h of x equals x plus 5 over 2x squared plus 11x minus 6 is undefined. And undefined is when the denominator would equal 0. So let's take that and write an equation and actually solve it for x. Let's set the denominator equal to 0. Solving for x, we'd have to do the rainbow. Get negative 12. Factors of negative 12 that sum to 11 are positive 12 and negative 1. Let's do our grouping of our 4 terms and split. 2x, x plus 6 is the other factor, minus 1, x plus 6. We have x plus 6 times 2x minus 1. Set each factor equal to 0. So x plus 6 equals 0, 2x minus 1 equals 0, x equals -6, and x equals 1/2. So it's these two values. So -6 and positive 1/2. Verify by using the calculator to evaluate the expression for these values. I'm just going to put it into y equals, right, and I have it in there already. If I look at the table of values, value of -6 gives us an error. And a value of 1/2, I'd have to change the table. I'm doing second window, and right now the table is going by 1, so I'll do by 0.5, so that we'll be able to see a half. Value of 1/2 in for x also results in an error. Which of the following represents the domain of the function? Okay, again with these, you can put any value of x in the numerator and still get out a real number. With the denominator, any value of x except for whatever is going to cause this denominator to equal 0. Because when we have something over 0, anything over 0 is undefined. So let's just take this and, okay, when does it equal 0? What are the factors of -16 that sum to -6? -8, positive 2. Set each one equal to 0. So the domain would be any real number x such that x does not equal positive 8 and -2. If we put a -2 in here, we'll come out with a value of 0. And we can't have 0 as a denominator. It's just not a real number. So choice 3. Next, page 296. Find the formulas for the inverse of each of the following rational functions. Okay, so we're finding the inverse of rational functions here. We found inverses of linear functions before, and to find an inverse, it's always 2 steps. You switch x and y, and then we solve for y. Well, now we have a rational function, so we do the same. We switch x and y, just a little more complicated in solving for y, that's all. X equals y over y minus 2. Then we're going to cross multiply. We have x times y minus 2 is equal to y. Distribute x, if it applies. Distributing xy minus 2x equals y. Now we want to move the terms with a y to the left, right? And move the terms without a y to the right. Okay, so y terms we want to the left and non-y terms to the right. So I'm going to subtract y. I'm going to bring this term containing y over to this side. And in the same step, well, no, I'm sorry, I'll do this one at a time. We have xy minus y minus 2x equals y. And, I'm sorry, equals 0. Y subtract y is 0. And then add 2x. Let's see if I get this right. We have xy minus y equals 2x. So we have our terms containing y on the left-hand side and our non-y terms on the right. Now we factor out y. Y is common to these two terms on the left. We have y times x minus 1 equals 2x. And now to get y by itself, we undo this multiplication by dividing. Y equals 2x over x minus 1. So this is the inverse. So let's look at B. Switch x and y. X equals y plus 3 over 2y. Put that over 1, cross multiply. X times 2y is just 2xy. Let's move this term of y over to the left-hand side by subtracting y. Now 2xy subtract y, they are not like terms. So they do not combine. Okay, now factor out a y here is common. We have y times 2x minus 1 equals 3. We have y times this, divide by 2x minus 1, y equals 3 over 2x minus 1. So try pause the video, and if you would, try number 5 on your own. Switch x and y. I'm going to run out of room there. I'm going to move it over to here. Cross multiply. Bring the y terms to the left, non-y to the right. Left-hand side, my two terms containing y factors out. And then we divide by x minus 2. And this matches choice B. I'll explain in class that there's always two acceptable answers to these inverse of rational functions. There's what you end up with, and if you've gone about things differently, also would be acceptable is negative x minus 1 over 2 minus x. All right. Page 299, simplifying rational expressions. To simplify a rational expression, what we want to do is we factor the numerator and factor the denominator and divide out common factors. So we factor the numerator, factor the denominator, divide out common factors to simplify the given fraction and rational expression. So first, a numerical fraction. We want to simplify 18/12. Well, I could rewrite this. We could rewrite this as 6 times 3 is 18, and 6 times 2 is 12. And then the common factors of 6, common to numerator and denominator, would divide out, and our answer is 3/2. We want to do the same when we are faced with a rational expression. Factor this numerator. This is the difference of perfect squares, x plus 3 times x minus 3. The denominator, there's a GCF of 2 that factors out, x plus 3. And then we just put a slash through the common factors. Don't scribble them out or erase them. So what's left is x minus 3 over 2. So this has been simplified. When we simplify fractions, the numerator and denominator must be factored, and only common factors, you must factor first, and then only common factors divide out. This is true whether our fraction contains a monomial, binomials, or polynomial expressions. All right, so here we have some monomial expressions. So again, there's more than one way to go about this. I could look at the numerator and say, okay, so we have a 3 times x to the 5th times x to the 3rd, or sorry, y to the 3rd times y to the 3rd. So the only thing I split up here was the y to the 6th is equivalent to y to the 3rd times y to the 3rd. And now the denominator, 6, here we have 2 times 3. We can rewrite 6 as that. X to the 8th can be written as x to the 5th times x to the 3rd. And y to the 3rd just stays. And now we can divide out common factors. The 3's divide out. And again, these have to be common to a numerator and denominator. The x to the 5th and the y to the 3rd. And we are left with y to the 3rd over 2x to the 3rd. Do you have to do it that way each time? No. I know a lot of you can do this mentally, all right? Like the 7 and the 21. Oh, 7 goes into 21 3 times. But if I continue in the way I started, x to the 5th I would break down into x to the 3rd times x to the 2nd, and y to the 8th would be y times y to the 7th. And then there are common factors that divide out, common to numerator and denominator. And this would leave us with 1 over 3x squared y to the 7th. Now for number 3, okay, instead of doing the long process, let's try this. The 10 and the 5, go with those coefficients first. 10 and 5 both have 5 in common. Dividing each by 5, we get 2 and 3. X to the 6th, x to the 7th, or sorry, x to the 2nd. X to the 6th is x to the 2nd times x to the 4th. So x to the 2nd divides out with an x to the 2nd in the numerator, leaving us with an x to the 4th. Y to the 3rd in the numerator. Let's take y to the 3rd out of y to the 6th, and we're left with y to the 3rd in its denominator. Our answer is 2x to the 4th over 3y to the 3rd. Option 3. And number 4, simplify. 9x squared plus 3x divided by 3x. We factor the numerator, factor the denominator. Well, the denominator cannot be factored, but the numerator can. There's a GCF 3x, and we get 3x plus 1. Denominator remains 3x, but 3x is common there. It's a numerator denominator, so it divides out. So this simplifies to 3x plus 1. For time purposes, I'm going to skip B and C and go on to page 300. Again, can't be stated enough, when simplifying rational expression, always factor first, then divide out common factors. And these are common factors to numerator, denominator. Simplify each of the following. take this trinomial, factor it. Take the denominator, the difference of perfect squares, factor it. So our trinomial, the factors of negative 14 that sum to 5 are 7 and negative 2. And this is x plus 7 times x minus 2. And the denominator, the difference of perfect squares, factors in x plus 2 times x minus 2. The x minus 2's are common, they divide out. It simplifies to x plus 7 over x plus 2. Can you divide out the x's? No, because this is plus. It's not multiplication. With b, again, factor the numerator. This is the difference of perfect squares. 2x plus 1 times 2x minus 1. There's a GCF in the denominator, 5, and 2x minus 1. The 2x minus 1 binomials are common, they divide out. Our simplified answer is 2x plus 1 over 5. C, the trinomial in the numerator, we'd have to do the rainbow, that's 24. Factors of 24 that sum to 14 are 12 and 2. So we have 3x squared plus 12x plus 2x plus 8. And splitting, 3x comes out as a GCF, x plus 4 in parentheses, and 2x plus 4. Okay, so this factors into x plus 4 times 3x plus 2. And the difference of perfect squares, x plus 4 times x minus 4 for our denominator. Plus 4, whoops, wrong one. Plus 4 is divided out. Keep this one. 3x plus 2 over x minus 4. So all that factoring we did back in Unit 6, I got to bring it back to you here in Unit 10. Alright, and the last thing we're looking at is a special type of simplifying occurs when an expression of the form x minus y and y minus x are involved. Simplify each of the following. If we have 9 minus 6, these are like terms. That's equivalent to 3. Divided by 6 minus 9, which is equivalent to negative 3, we end up with negative 1. 15 minus 3 divided by 3 minus 15, that's 12 over negative 12 equals negative 1. A minus b times b, or divided by b minus a, well, a minus b divided by b minus a should be negative 1. I call these opposites. If I think of this, this is a positive a and a negative b divided by a positive b and a negative a. The opposites. So opposites like this are going to simplify to negative 1. Which of the following is equivalent to? Okay, so in other words, we want to simplify this. Factor the numerator, there's a GCF 2. Factor the denominator, the difference of perfect squares, 5 plus x times 5 minus x. This only works when it is subtraction, not addition. So this x minus 5 and this 5 minus x, these are opposites. Right? So they're going to divide out, these are opposites. I usually write the word. That's a positive x, negative 5, positive 5. So they divide out and are replaced with negative 1. Now the negative can be placed either in the numerator, in the denominator, or out in front of the fraction. I'm going to keep it in the numerator, negative 2 over 5 plus x. And just realize that 5 plus x is the same as x plus 5, choice 1. And lastly, factors of positive 9 that sum to negative 6, negative 3, negative 3. X minus 3 times x minus 3. And 6 is common here. We have 3 minus x. The 3 minus x in the denominator factors out with one of the x minus 3 in the numerator, replacing it with a negative 1. We have negative parentheses x minus 3 over 6, and distribute that negative so that we can match one of our 4 options, negative x plus 3 over 6, which is the same as this, choice 4. Negative x plus 3 is the same as 3 minus x. Thank you very much for your attention.